and this is on page 16 of your unit handout. Really, the first derivative test is what we've been doing. We just haven't been calling it a first derivative test. We've been saying you can use the first derivative to determine where a function is increasing and where it's decreasing. And in the previous lesson, we kind of tied that together and used where it's increasing and where it's decreasing to determine where there are maximum values of a function and where there are minimum values of the function. So if we start off with the assumption that we're dealing, in this lesson anyway, with functions that are continuous at some value of x, we tend to use c because c is a critical number. The critical number statement in this sentence you're looking at right now is the same definition as what we've been talking about for a couple of days. X equals c is a value of x that makes the derivative either equal to 0 or makes the derivative not defined. If we assume that a function is continuous as we go through that critical value, so there's no asymptotes, there's no holes, there's no funny business going on, then two things must be true. If the first derivative changes from being positive to being negative through c, which means immediately before c, the first derivative is positive, and immediately after that x coordinate of c, the first derivative is negative, then a maximum value of the function has to exist there. Because if the first derivative goes from being positive to negative, the derivative goes from increasing to decreasing. So before c, you're walking uphill. After c, you're walking downhill, which means at c, you were at the top of the hill. Similarly, or conversely, if the first derivative changes from being negative to positive as we go through point c, then a minimum value has to exist. So if you're going downhill because the derivative is negative, and then immediately after some point you're going uphill, then at that point you must have been at the bottom of a valley. To illustrate this to you, and there's no need to write this down, you can look at it in video form later if you need to digest it more. If you make a first derivative table or chart, and you've identified the intervals on the left-hand column based on the critical numbers, and you don't make the mistake that I made in our last example in the previous lesson, you're careful to put them in the right order, then you can complete this by determining where the derivative is positive and where it's negative. So let's just imagine that you get positive for the first interval, positive, then it becomes negative, it becomes positive again, and then it becomes negative. Well, that tells you something about the function. It tells you the function is increasing because the derivative's positive, then it's continuing to increase, and then it decreases over this interval, increases in this interval, and decreases in that interval. Well, let's just call these intervals something so I can refer to them. The function increases in interval a, and then at some critical value of x, it immediately increases again once it passes that critical value of x. Nothing interesting is happening as the function goes from a to b, even though there was a critical value of x in between. But when the function goes from interval b to c, the function goes from increasing to decreasing, which means there must be a maximum value there. If the function is decreasing in interval c, and then immediately as it passes into the next interval it's increasing, that must have been a minimum. And if it's increasing in d and then decreasing in e, it must be a maximum. I hope that makes sense. Really, that's just a summary of what we did in the last lesson. We have two examples. Find all maxima and minima for the following functions. If f of x equals 3x to the 5 minus 5x cubed, what are the coordinates of all of the maxima and minima values? The first thing that I want you to note, everybody, is that this is a polynomial function. And what that means is, well, it isn't that it's polynomial, although that's true. When you look at that function, the domain is any real number. positive numbers, negative numbers, 0. You can do it all with this function. You can take any number and put it in without violating any laws of mathematics. Which means when we do find our critical values of x, in order to come up with a first derivative chart, we are going to start slicing up the domain of all real numbers using the critical values of x. So let's find the derivative first. It will be 15x to the 4 minus 15x squared. Swinging the 5 down, 5 times 3 is 15. Drop 1 from the exponent. Swing the 3 down, 3 times 5 is 15. Drop 1 from the exponent. The derivative in that form is really useless to us. It only becomes valuable in factored form. So I can factor out a 15x squared and be left with x squared minus 1. I can factor further into x plus 1, x minus 1. Now, what are our critical values of x? Our critical values of x are 0 because of the factor of x squared, and plus or minus 1 because of the factors x plus 1, x minus 1. I want to make a little point here. I know that everybody can look at this form of the derivative to figure out those 3 critical values of x. I know that you don't have to write x plus 1, x minus 1 to know that the critical values are 1 and negative 1. But you should, you don't have to, but you should have it in factored form, because when we create our first derivative table, it will make your life easier. So we're going to cut this at negative 1, at 0, and at positive 1. Our intervals will be negative infinity to negative 1, negative 1 to 0, 0 to 1, 1 to infinity. So we build that chart. Negative infinity up to negative 1, negative 1 to 0, 0 to 1, 1 to infinity. A couple of checks here, which I didn't perform in that last example in the previous lesson, which is where I went off the rails. If we have a certain number of critical values of x, you should have one more interval. So if we have 3 critical values of x, we should have 4 intervals. The other thing is the x numbers need to go from small to big. So when I look at these, I have negative 1, then it becomes 0, then it becomes 1, then it becomes infinity. So they are all increasing and they're in the proper order. Across the top, we can put all of the factors of the derivative, which will be, I'm not sure that the 15 needs to be written down, but there you go. Now we're going to go x plus 1, x minus 1. The derivative is the next column, and y is the final column, which is telling us what the function is doing. I'm treating the 15x squared as one factor. This, I think, is our first encounter of something that doesn't go positive to negative or negative to positive. And the reason is it's x squared. Now, I'm going to write something down, but I don't want you to write it down, because I'm just going to revert back to what you're looking at here. I have seen textbooks, and I think your textbook is one of them, do the following. They take the 15x squared and they break it into 15 and x, which is, it kind of makes sense. You're writing all of the factors. And x is negative, negative, positive, positive, and then the other x is negative, negative, positive, positive. And what's going to happen is when you multiply these negatives together, you're going to get positive. So my advice to you is that whenever you have a factor which is raised to an even exponent. Let me get back there to where it was. You have a factor which is raised to an even exponent. Just write it down and put positives, because when you square something, or you raise it to the 4, you raise it to the 6, it's going to be positive. Now, this x plus 1, x minus 1, you could make the same argument. Don't erase anything. You could make the same argument that, well, why don't we just put x squared minus 1? The answer to that is it becomes more complicated as to whether x squared minus 1 is positive or negative. So it's much easier on the brain to separate them out in this case. I have seen some texts where they just do the whole derivative in one shot. In other words, they don't even have columns. They just say, is the derivative positive or negative in each interval? Break it down so that you're able to get this final column accurately. Back to reality of this table. This will be negative, then it's positive, positive, positive. Remember that the factor, in this case x plus 1, will switch from negative to positive as it passes through the 0 of the factor. And it goes from negative to positive because the leading coefficient on x is positive. If the leading coefficient on x were negative, it'd be backwards. Negative, negative, we still haven't reached the 0 of x minus 1. We're just about to pass through the 0 of x minus 1, which is 1, which means it switches. Then you multiply across the top. 2 negatives and a positive is positive. 2 positives and a negative is negative. Negative, positive. I like to circle the sign I put under dy dx, because then I can distinguish that it's a separate kind of thing. It's the conclusion to those other things. So that means since the first derivative is positive in that interval, the function is increasing, then it's decreasing, then it's decreasing, then it's increasing. So what does that tell us? It tells us there's a maximum here. And when I say here, I mean at x equals negative 1. And there's a minimum here. And when I say here, I mean at x equals positive 1. Was there a critical value of 0? Yes. Was 0 corresponding to a max or a min? No. So again, all of the max mins turn out to be critical values, but not all critical values gave us a max min. We can answer the question now by going back up here and saying there was a max at negative 1 comma something. There's a min at positive 1 comma something. I'm just taking that information from my table or chart. And now we find the y coordinate. And you find the y coordinate by using this function. So you put negative 1 in for x, and then you put positive 1 in for x. When you put negative 1 in for x, I'm just going to give myself a bit of workspace here. When you put negative 1 in for x, I'm sure most of you don't need to write this down, but I don't want to leave anybody behind here. You're going to get negative 3 plus 5. You're going to get 2. And then if you were to put in positive 1, you would end up with 3 minus 5. You get negative 2. So there's a minimum at negative 1 comma 2. There's a maximum at positive 1 comma 2. Any questions with the first example, A? Pretty simple to check that. This is quite a high degree for a polynomial function. It's degree 5, so we might have to play around with the zoom settings here, but it's 3x to the 5 minus 5x to the 3. I'm going to start by adjusting my window settings to go from negative 2 to 2. We won't worry about why I'm doing that. I'm going to go negative 10 to 10. I don't think that might not be too bad. Now I'll take a look at the graph. This is what the graph looks like. Kind of a wild polynomial function. If you were to find if you were to find the coordinates of that maximum point over here on the left, you would discover it's at -1, 2, and the coordinates of this point on the right, you would discover it's at 1, -2. So there's a way for you to check it on your graphing calculator. Let's move on. Let's take a look at B. Fairly simple looking function. F of x equals 1 over 1 plus x squared. Again, I just want to make the observation that this function is defined over all real numbers. There are no asymptotes. There's no way that 1 plus x squared can be equal to 0. There's no asymptotes. There's no square roots. It's defined over all real numbers. Let's find the derivative. First of all, in order for me to find the derivative, I would much rather think of this as the function. If you're going to use 1 over 1 plus x squared, and some of you will, and that's fine, you're just going to have to remember that when you use the quotient rule, the derivative of the top will be 0. Since the top is a constant, to me it's easier to move the bottom up and express it with a negative exponent. I don't even have to use the product rule here. I just use the power rule. I sweep that -1 out in front of the base, which stays the same. I drop 1 from the exponent, and I multiply by the derivative of what's inside. This should be a 2. So I bring the -1 down, base stays the same, drop 1 from the exponent, multiply by the derivative of what's inside. In order to make sense of this, we're of course going to write -2x over 1 plus x squared, quantity squared. There is only one critical value of x, and that's 0. Just take a minute and roll that around upstairs in your head. There's no value of x that makes the derivative undefined, because undefined would mean you're solving this. You're saying, what value of x makes the bottom 0? Well, that's impossible, because then you would get x squared equals -1, and to find x you would take the square root of a negative, which is hands off. You can't do that. So the only critical number is the one that makes the derivative 0, which is 0 because we have a factor of x in the numerator. Our chart then is going to be pretty basic. We're going to go from -infinity to 0, from 0 to infinity. Across the top, we'll have -2 and an x and 1 plus x squared. You know, I prefer to treat the -2 and the x as one thing. Let me write down what would happen if you treated them as two things, and then I'm going to go back to treating them as one. -2 is a constant. It's negative everywhere. X is negative here and positive there. So when you end up multiplying these, -2x is positive, then negative. Well, -2x is a linear factor with a negative coefficient, which means it goes from positive to negative as it passes through the 0. You know, again, everybody, quite frankly, I don't care how you break this down across the top, as long as you end up with correct columns for dy, dx, and y. Obviously, if it's an assignment, you need to show your work. So I don't want to just see these last two columns. 1 plus x squared, quantity squared, is always positive because you're squaring something. Well, and it's also positive because 1 plus x squared would always be positive. So you know what? Even if this were 1 plus x squared cubed, it would still be positive everywhere, because 1's positive and x squared is positive. Multiplying across the top, plus times plus is plus, And on the bottom column or bottom row, negative times positive is negative. The function is increasing, then the function is decreasing. So right here we have a max. That means that that critical number of 0 is where a maximum occurs, and the max will be at 0, comma f of 0. So if I put 0 in for x into that function, I'll have 1 over 1, which is 1. There's a max at 0, comma 1. And if I had to guess, I believe this graph is going to look like the following, something like this. We'll have an asymptote here, and it will cross the y-axis with a maximum value at 1. Let's just take a quick peek. 1 over, in brackets, 1 plus x squared. Yep. So that's what it looks like. Again, the work we do on paper is borne out by what your graphing calculator actually shows you. So that's it. And I didn't include a lot of examples in this lesson because, quite frankly, you know what it is you need to do now to find max mins. You find the derivative so that you can identify all of the critical numbers. You use the critical numbers to identify all of the intervals that you're going to put in your first derivative chart. You find out whether the derivative is positive or negative based on that chart in each of those intervals, and then you go from there. Does anybody have any questions with that last example? All right, like I said, it was a short lesson, not much really added. Too fast, too slow, or just right for that last little lesson? Thank you. So there's lots for you to practice here. 1 to 4 on page 182 and number 3 on 196. Anytime it asks you to sketch a graph of the function, you absolutely do not have to do that. It might be useful for you to double check and help visualize things, but in chapter 5, we have a whole chapter that's based on graphing that we learn how to graph, so I wouldn't worry about it. Yeah, get to work. Don't forget you have that assignment. I have most of them in, but you have assignment 2A, which is due in an hour and 20 minutes. And I don't really care if you're here till 3:15 or 3 o'clock. If you feel you got everything out of today from me that you need to, feel free to move on in your life, but I'll be here till at least 3:15.